Welcome back. This is a continuation of our lesson on sets. So in the previous video, we look at a set of real numbers. We saw that a set of real numbers, which is denoted by capital R, is divided into two basic numbers called rational numbers, denoted by this capital Q, and irrational numbers, capital H. And then we saw that the rational numbers is further divided into what integers and what fractions. And then the integers is also divided into what whole numbers and what and negative numbers. So yeah. So and then we also represented everything on what on a number line. Represent the whole real numbers or set of real numbers or what on a number line. And then we said that usually in the set of only we draw a number line, we don't bring what do we call, we usually bring only the integers on the number line. And at times we bring or we also add decimals. Decimals like 0.5, 1.5, 2.5, negative 0.5, negative 1.5, negative 2.5. But usually we don't bring decimals and what and fractions on the number line. So let us continue and look at what a set of rational numbers as a topic on this one. So yes, as I said, students, let's look at the set of what rational numbers as denoted by what capital letter what Q. So what is a rational number? We are saying that what a rational number is a number. A rational number is a number which can be expressed as a ratio of two integers. We are saying that the rational number Q is any number which can be expressed as a ratio of what two integers. So if we define, we are in the set of using the notation of sets, then we can say that the set of rational numbers Q is equal to what? S is standard, S is equal to what? P over Q, where Q is not equal to 0, and what P and Q belong to what? The set of integers. So that is what we are saying. So we are saying that Q should not be equal to 0. Why? Because if Q is equal to 0, then the rational number will be undefined. So Q should never be equal to 0. Yes. So we are saying that note the set of real numbers, set of integers Z is equal to giving out, yes, as we said, you saw in the previous lesson. This is what we have 0 and then 1, 2 counting numbers to infinity, and then negative what? Negative numbers to infinity. This is the composition of what? The set of what? Integers. Since every integer n, we are saying that since every integer n in general can be expressed as what? The ratio of what? N over 1, then it means that every integer n is a rational number. All these numbers here can be represented as what? N over 1. So any number over 1 is the same as that number. So we can say 1 over 1, 1, 2 over 1, 2, 3 over 1, 3. Negative 1 over 1 is 1. Negative 2 over 1 is what? Negative 2. And so on and so forth. So we are saying that since every integer can be expressed as what? Every integer n, since every integer n can be expressed as what? N over 1, or is the same as n over 1. We are saying that what every integer is what? Is a rational number. So we are saying that therefore the set of rational numbers Q is made up of what comprises integers and what positive and negative what fractions. Integers and what positive and negative what negative fractions. So let us continue. Thank you for watching it. See you in the next video. Hello students, as we said in the previous lesson or video, that a set of rational numbers, therefore a set of rational numbers Q is made up of or comprises integers and what positive and negative what negative fractions. Yes, so that is what we saw in the previous video. That's what we saw in the previous video. So if you have this, you draw this a number line, we have the integers, the 0, we have 1, 1, 2 going to infinity, and we have for negative 1, negative 2 going to infinity. And we also have fractions here. It's negative 1 over 2, and sorry, this is negative 3 over 2, and then this is negative what 1 over 2, and we have this is 1 over 2, positive 1 over 2, and this is what positive 2 positive 3 over 2. So we are saying that the set of rational numbers is made up of what? The integers and what? Positive and negative what? Fractions. Positive and negative what? Fractions. Yes. So let us continue. Example. Let us look at what examples. Examples are 2. We are saying that a rational number is any number that can be expressed as what? A ratio of 2 integers. So 2 is the same as 2 over 1. So which means that 2 is a rational number. we have 7 over 250, which is also a rational number. 7 over 4, 1 over 6, 1 over 3, 25 over 7, and the square root of 9. Square root of 9, you know, this is what 3, so it's an integer of the whole number, which is what a rational number. And then the same with square root 25 is also what 5, which is also what also a rational number. Note that the decimal equivalent of a rational number either terminate or what repeat. So okay, let us look at these examples. There's a unique the feature about what or characterizes about a set of what or rational numbers or a rational number. So 2 is a rational number which is the same as 2 over 1. And that one get 2 is the same as 2. 7 over 250, which is what a fraction, which is a rational number. The decimal equivalent, which is also a rational number, is 0.028. Then 7 over 4, and it's a rational number, which is a fraction, and its decimal 1.75 is also a rational number. So, however, if you consider 1 over 6, 1 over 6 is 0. What? 0.1666. So you know that you see that this 6 is repeating to infinity. It will never end. It will go on, go on, go on, go on. So if you use your calculator to punch this, then because of depending on the capacity of your calculator, it will terminate at a certain point. But this 6 goes through on the yes, it goes without ending. It does not end. It repeats. So since if you look at it, you notice that 0.16 the 6 that is what is the 6 that is repeated. So normally what we do that we do is that we put this dot on top of what stage. So 0. What 0.16, then we put dot here. This is the same as the 6 repeat, the same as 0.1666 going to what infinity. So in order to just be able to write it in a short form, you just put this dot at the top of it to tell you that the 6 was repeating. And the same with 1 over 3 is 0.3333. So now the 3 will go on without ending. Have you seen? And to shorten it, you see, you write 0.3 and put this dot on top of it to tell you that the 3 is repeating. The same with square root of 36, which is what? Square root of 36 over 1 is equal to what? 6 over 1, which is equal to 6. It's also what? A rational number. If you look at this number, 25 over 7, you get what? If you use your calculator to punch this, you get 3.571428. Have you seen? 3.571428. 571428. So this 571428 also repeat. 28, and then we get 571428. So to be repeating up to infinity. So what we can do is that we can write it in a short form. You can say 3.571428. So it is the whole of this thing is what repeating. So what we do is that we put dot on 5 and then we put 1 dot on it to tell you that this whole thing is what keeps on repeating. So that is the short form. So what do you notice? You notice that the decimal equivalent of some numbers terminate. So this one 2 over 1. The decimal equivalent just 2, just terminate or ends. And then 7 over 25. This is what 0.028. This is it terminates or ends. This one also terminates. But this one does not terminate. It keeps on repeating. It's recurring. Yes, it's recurring. 1 over 3 is also 1 over 6 is what is a recurring decimal, or the decimal equivalent of this fraction is what is recurs or repeat, and the decimal equivalent of this what fraction also repeat. Yes, and this one too, that's 25 over 7 also that's what also repeat. So that we are saying that is the decimal equivalent of a rational number either terminates or repeats. So all these are examples of rational numbers. So if you find the decimal equivalent of a rational number, it will either terminate or repeat. So this one is an integer or whole number. So this one is not a decimal. Obviously, if you want to write it in a decimal for the same as 2.0, obviously, which is the same as 2. But we are saying that the fractions and the fractions, whenever you find their decimal equivalent, they will either terminate or repeat. So this one is a terminating decimal. This one is terminating. This is a recurring or repeating decimal. So we are saying that the decimal equivalent of a rational number either terminates or repeats. So that's what we mean by that. So let us continue. Let's see you in the next video. Oh, you are welcome back. So let's look at, so you are saying that how about consider the following. Let us consider the following. That's what about square root of 20. Square square root of 20. If you use your calculator to calculate it, you get what 4.42. Sorry, 4.472 135 954 999 5793 9281 is going to infinity. So, but what do you discover here? Do you see any pattern here? No, you see that this one, though this one will keep on, the decimal will keep on, going to infinity, but you don't see any pattern that this one is not. Well, first of all, we can say that they are not terminate. The decimal equivalent of it are not terminate because the numbers keep on repeating. But it also doesn't repeat. They are not recur at any point. No number keeps on repeating. Everything. So the decimal equivalent of this that neither terminates nor repeats. The decimal equivalent of this number under the square root sign neither terminate nor repeat. The same way, square root of 2 is 1.4142 1356. You see, so this one does not terminate and it doesn't what, and the numbers also don't repeat. So neither terminating nor repeating. Oh, so what do we notice? What do you know? That's the question you are saying. The decimal equivalent of these numbers neither terminate nor repeat. Obviously, the decimal equivalence of these numbers at the top here neither terminate nor repeat. Such numbers are called irrational numbers. So these numbers are called irrational numbers. So we are saying that in general, square root of prime numbers are irrational numbers. The square root of prime numbers are irrational numbers. So when we were looking at what do you call it? When we were looking at the number line, you see that the number line we represented all this represent we represented what do you call it? The set of real numbers on the number line. Have you seen? And then you said that the numbers under the square root sign they also included. So these numbers are what we call these numbers are called irrational numbers, and these irrational numbers they are the sets. So these numbers under the square root sign they are the sets or the irrational numbers. That is so that's we don't know that. So just a minute. Let's go. Yeah, so as we were saying in the previous lesson, we are saying that in general, the square root of prime numbers, if you find their decimal equivalent, they will neither terminate nor repeat. They are called irrational numbers or sets. They are irrational numbers or sets. Yes, so that is it. Let us continue. So we are saying that you note the following. Product of two different irrational numbers is what? Is an irrational number. What we are saying that if you multiply two irrational numbers, the result or the answer will also be what? Be an irrational number. So the square root of 2 is an irrational number. Square root of 3 is an irrational number. If you multiply them, you get square root of 6. That is what? An irrational number. Amazing. So we are saying that the product of two different irrational numbers what is an irrational number. Any irrational multiple of an irrational number gives irrational number. So all we are saying that if you multiply a rational number, 2 is a rational number, square root of 5 is an irrational number. So if you multiply a rational number by irrational number, the answer or the result will be an irrational number. So definition of a set. So as I said, definition, we are now looking at what the definition of a set. So what is the definition of a set? We are saying that a set is therefore an irrational number, such as what? Square root of 2, square root of 3, square root of 5, square root of 7, square root of prime numbers, etc., which involves square root, whose decimal equivalent neither what terminates nor repeats. So that is the definition of a set. So a set, sets are irrational numbers. They are irrational numbers. Because they are irrational numbers, if you find their decimal equivalent, they will neither end or repeat. They will neither terminate or repeat. So sets are just irrational numbers. And then these irrational numbers are the square root of prime numbers and the square root of product of numbers involving or prime numbers. Those are irrational sets or irrational numbers. Thank you for watching and see you in the next video. Don't forget to subscribe to the channel, hit the bell notification icon so that you'll be notified if additional videos are uploaded. Keep your comments also coming. Whatever question you have asked, you can also contact me on WhatsApp. Yes, so student, what you have to do is you have to create a special email for the channel so that you can also subscribe with the email. Whenever you are subscribing, you will have to enter your email address. So just get an email address for subscription on the channel. Yes, thank you for watching and see you in the next video.